All right, so we've talked about what linear operators are and why linearity is important. We've also discussed how these relate to a general method for solving linear differential equations. And that method we have has two parts to finding the solution, a general solution, and then if you're given enough initial conditions, you can find a unique solution to an initial value problem. So what we're going to focus on now in the next 5 short videos is we're going to walk through how we find the general solution of the homogeneous problem. Now this was the problem where we take our linear differential operator L and we solve the equation L of y equals 0 and find a general solution of the form y sub h, where y sub h is going to be some sum of terms, each term being a solution to the homogeneous problem. And then by putting constants in, we can construct a general solution. So if the equation is order 10, we would have 10 terms, and each term would have its own unknown constant. And then if we had 10 initial conditions, we can put those into a system of equations and determine the exact values of those constants. In this video, I want to just talk about the observation that we're going to make to solve these homogeneous equations, L of y equals 0, by basically just making an algebraic observation. And then in subsequent videos, the next 4 after this, we will go through second order equations and look at the different types of problems you can run into, and then we will finish off with some examples of each. So we're going to focus on linear homogeneous equations with constant coefficients. So these are going to be equations where, if you recall from our formula, we have some functional coefficients, p0 of x, p1 of x, each of these being multiplied by either y or some derivative of y. We're going to just assume these are fixed numbers, just constants. So we have our general equation, L of y equals phi of x, where phi of x is some given function. All right, and we may have n initial or boundary conditions, since this is an nth order equation. Again, we're going to focus mainly on second order because there's really no extra complication in doing higher order equations. The method is exactly the same. It just becomes a little more complicated and you have to solve for more complicated algebraic equations. So recall our general method. We're going to find two parts of our general solution y. We're going to find a particular solution to this equation we have here, and then we're going to find another general solution to the homogeneous equation, L of y equals 0. And that's what our focus is going to be on for this and the following 4 videos. We'll focus on finding what this particular solution yp is in later weeks. So the idea is, because it's an nth order equation, the homogeneous equation with constant coefficients will allow us to find n different functions, y1, y2, and so on. And from these we construct, because of the linearity of y, we just add terms together with different unknown constants to construct our general solution to this homogeneous problem, which we call y sub h. Again, we're going to identify these functions as independent. And your book talks about this, and you'll learn more about independence in a linear algebra course. But for our purposes, the functions we find are going to be independent, so we're not going to really have to verify that in any way, that it's going to happen. So in general, we're going to have to find n of these functions satisfying our homogeneous equation so that we can construct y sub h. But finding these, we're going to see, is actually quite easy. But we're going to go through and explain this process a little bit so you have a better idea of the big picture as we're going through. But in the end, once we watched this video and the next 4, it really comes down to solving this homogeneous equation is actually very easy, and it just requires you to make some algebraic observations. So again, a linear homogeneous equation is any differential equation of this form where the right-hand side is just 0, the 0 function in this case. So we're just saying L of y is some function that y is transformed into. It has a particular form because we're considering L as a linear differential operator. And we're going to say that it has to equal the 0 function. So we want to solve this. So again, just to keep in mind what these words mean, This example equation is a linear homogeneous equation. It has second derivative plus x times the first derivative plus cosine x times the function y. Now remember, this notation here, don't get confused. We really need to use parentheses. When you're using trig functions or natural logarithms, if you're going to input more than one character, in this case xy is two characters, you really need to use parentheses to emphasize that. If you're not going to use parentheses in these things, then only the first character is part of the cosine. So this is cosine x times y. If you wish, write the y in front of cosine x to make it clear, or just use parentheses. Now this equation is linear. It has the linear format on the left side. All right, it's first order. But the right-hand side is not the zero function, so it's not a homogeneous equation. It's not a linear homogeneous equation. And this next function is just not even linear because of the term y prime y. That multiplication of y and one of its derivatives, or even a power of y that's not 1, or a power of a derivative that's not 1, that leads us to conclude that it's not a linear equation. Again, remember what homogeneous is not the same as we talked about earlier. It's referring to the operator L. The idea being, because it's a linear operator, the homogeneous equation, L of y equals 0, if y is a solution to that, then any multiple of y is also a solution. And that is the idea of homogeneous that we're talking about here. That you can basically multiply your solution to this equation by any number, and it doesn't change the fact that you still have a solution. But also it's linear, so we can add multiples of other solutions and create new solutions as well. This is just what we're just illustrating here is what homogeneous means. Because I have a solution y, we know that any number times 0 is 0, so we can write that down. But 0 is L of y by our assumption that L of y is the 0 function. And because L is linear, we can bring constants inside and outside of L, and that's just confirming to us what homogeneous means, is that if y is a solution to the homogeneous equation, then so is any multiple of y. Again, back to linearity. Because of the fact that we have 0 on the right side, we can find multiple solutions possibly. Again, in general, if it's a 10th order equation, we're going to find 10 different solutions. And we can add combinations of those together with different coefficients and can create a new solution. So for example, if I have two functions, y1 and y2, which both solve my equation, then I can create any combination of these, any linear combination of these, which is just a constant times one of them plus a constant times the other. In this case, we're adding 5y1 plus a negative 2y2. That is also going to be a solution because of the linearity of L. That's really why we like to use linear operators and focus on them, because of this algebraic simplification. Again, just illustrating how linearity works in this case, to confirm that we've constructed another solution from the first two. So in general, we can put any constants to create a new solution of the homogeneous equation. When we're talking about the non-homogeneous equation, where the right-hand side is some function like phi of x, or x squared, or x cubed, or e to the x, anything, you can't use this. You can't add solutions together, because if you add solutions together, you're going to get a multiple of the right-hand side, and that's not equal to the right-hand side, but a multiple of 0 is still 0. So that's why this works for the homogeneous equation. So the main observation that we're going to make is that of what are called characteristic equations. When we have an nth order linear differential equation, so L of y is being defined as this expression here. If we set that equal to 0, that gives us a homogeneous linear equation. And in this case, we're only considering number coefficients, a0, a1, and so on. These are just numbers. And because they're just numbers, and our right-hand side is 0, we could always divide by the number we see in front of the highest order derivative to make that 1, and then just readjust everything. So we're going to always work with the first one being 1, first coefficient being 1. So the characteristic equation is just an algebraic manipulation and observation, where we basically translate our functional equation, which involves functions, into a numerical equation, where we replace y and its derivatives by powers of some numerical variable. I'm going to call it r because we're going to look for the roots of this equation, the numbers that make this equation true. Basically, remember what a root is. I have a function in some variable r. When does the graph of that function cross the horizontal axis? When that function is equal to 0. And that's what a root is. So notice what we're doing. The y is corresponding to our constant term. Y prime is corresponding to the first power term, and y double prime is corresponding to the second power term. So we're just translating derivatives into powers of this numerical variable, where taking no derivatives is like r to the 0 power, which is just 1. That's why we just have a constant a0. So what we're going to see is if we can identify the numbers r that solve this numerical equation, those numbers will tell us precisely how to construct the general solution of the homogeneous equation, L of y equals 0. To see this in action in a very simple, silly example is to consider first-order linear equation, which is homogeneous with constant coefficients. We already know how to solve these because these equations are already separable. If you reorganize them, you can see that such equation would have to be separable, and we could solve it very easily. But I'm going to use it to illustrate this point about characteristic equations. So we have an equation, homogeneous equation. We translate it into the characteristic equation, so 5 plus r equals 0, and we solve that, which is very easy because it's just a linear equation, r equals -5. Now, think back to how we would solve this equation using separable equations, and we find our solution very easily. We can see what that solution is. It's going to be some multiple of e to the -5x. Again, just plug e to the -5x into our equation up here, and you'll see that it is the solution. So this is not magical. This -5 being the root of the characteristic equation is exactly what we need to figure this out. We will see in the next video how this works for a second order equation. So again, we just confirm that this is the solution, but the point is we're connecting the idea of solving the characteristic equation numerically and seeing how that solution is going to help us determine a solution to our homogeneous equation. And again, the point is this algebraic observation is not an accident, and we're going to see how it works for second order next.